recap of week 1 and then we'll start off with some contents of week 2. Okay, so in week 1, we studied about the basics of vectors, how to add two vectors, how to do scalar multiplication on a vector, and all that we had seen. And since we knew how to deal with vectors, we also knew how to deal with matrices. So every row or column of a matrix can be viewed as a vector. So in that way, we knew how to add matrices. We also learned how to multiply two matrices. When can we multiply two matrices? What can be said about the order of the two matrices?
When the
Number of rows of first
column
should be
of
equal to
first
number of
row
columns.
is equal to the row of second.
The number of columns of the first one
Should be equal to number of rows of
so
second one.
yeah, should be equal to the number of rows of the second one. These two should be equal. Then we are allowed to multiply two matrices, and the product will be a matrix of order m cross p, m rows and p columns. Okay. And then what did we see? We saw system of linear equations. So we had equations which are linear in nature. That is, they didn't have any, the variables didn't have any higher power. They were all of degree 1. And with that, we solved a system of linear equations. So this was geometrically nothing but a set of lines. And then we found the point of intersection of the lines. So the three possible cases were the system may have a unique solution. That is, the lines will intersect at a single point. They all intersect at a single point. So in that case, we'll have a unique solution. When they don't intersect, there is no solution. And when the lines overlap, then there are infinitely many solutions. Yeah. And so, yeah, we had seen that when we have a system of linear equations, there are three possible solutions. One is three possible solutions in the sense, three possible cases for the number of solutions. And what else did we have after system of linear equations? Determinants, right?
Yes, sir.
Yeah. So how to find the determinant of a matrix? So how did we find the determinant of a matrix?
Solving a system of linear equation, finding them.
Eliminating the rows and columns and then multiplying the other.
By expanding along a row and all that, right? How did we find determinants by solving system of linear equations? What was that? Okay, fine.
Ma'am, we
so
solved the equations first in x, y, z form. Then we took out the coefficients and then we solved it.
Okay, I'm not able to connect to what you're telling. So,
मैम
yes.
मैम हम जो इसको लीनियर इक्वेशन को डिटरमिनेंट में बदल देते हैं, उसके बाद उसका सॉल्यूशन निकालते हैं, जैसे 3D वाला रहता है ना, 3D वेरिएबल वाला. तो 3D वेरिएबल.
Okay, that is converting, you're putting the system of linear equations in the matrix form and
Yes,
solving
ma'am,
it. Okay,
Yes,
okay,
ma'am.
fine. Yeah. So when you have, you can find determinant only for square matrices. And when you have a square matrix, you find the determinant by expanding along the first row or any row or any column for that matter, right?
Yes.
So this and all was discussed, and yeah, and we also saw that when you interchange two rows of a matrix, the determinant changes sign, right?
Yes, sir.
And
Yes.
when a row is multiplied by a scalar quantity, then the determinant also gets multiplied by that scalar quantity. And when you add a scalar multiple of a row to another row, the determinant does not change, right?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So when we do something like this, R1 is replaced with R1 plus alpha times R2 or something like this. In this case, the determinant does not change. So I hadn't told why this happened in the sense that, yeah, we hadn't discussed the proof behind this. There's one property of determinant which I will mention. Using that, you can easily see that because of this operation, the determinant does not change. Means when you do this operation, the determinant does not change. So the thing is, suppose I add, say A1, B1, C1, A2, B2, C2, A3, B3, C3. Suppose I have a matrix like this. The determinant of this matrix, if I'm going to add another vector to the third column. So this can be viewed as a vector, right? D1, D2, D3 can be viewed as a vector, right?
Yes.
I'm adding that vector to the third column of the matrix. This is actually equal to A1, B1, C1, A2, B2, C2, A3, B3, C3 plus determinant of A1, B1, D1, A2, B2, D2, A3, B3, D3. So when I write two vertical lines, it means determinant of that matrix. So this is a property of determinant, which is actually not, because of which the determinant does not change by this operation.
Excuse
So
me,
you
ma'am.
can actually expand and
Ma'am,
check that the determinants are equal in this case. Yes.
Okay, ma'am. Ma'am, can you please repeat?
Yeah. So this is one matrix whose first column is A1, A2, A3, B1, B, second column is B1, B2, B3. And the third column, I have sum of certain entries, C1 plus D1, C2 plus D2, C3 plus D3. This is equal to the determinant of the matrix where the first and second rows columns are as it is. The third column is split into this plus this. So you see that these two matrices are different, right? The third column is different, right?
Yes,
But
yes, yes,
ma'am,
ma'am.
Yeah.
excuse me, ma'am.
Yes.
Ma'am, in this A1, A2, A3, B1, there is a two matrix. We add them. So A1
No,
plus
no, no.
A.
This is not determinant of A plus B is equal to determinant of A plus determinant of B.
Yes,
This is
ma'am,
not that.
exactly, because the
This
first
is not.
two columns will be double in this case.
Yeah. This is not this. We had already seen an example where it is not equal, right? Determinant of A plus B is not equal to determinant of A plus determinant of B.
It's okay, ma'am, but in the two matrices, if we add two matrices, then we A1 plus A1, this is 2A1, na?
No, no,
So
this
These
is
are not
determinant.
matrices.
This is not a
They are
matrix.
determinant.
This is determinant of this matrix plus determinant of this matrix.
okay.
This is
Ma'am, how does
determinant.
So
it
this-
satisfy the first equation which you have written? The
This
column,
one, is it?
no, first one. The R1 changes by R1
Ah,
plus.
no. Ignore this for now. So this is a property. You can just expand and check that this happens.
Okay. This is clear,
Okay,
but
so
I just confused the O1 changes.
I will tell. I'll come to that.
Okay, ma'am.
So this is a property which you can check. You can just expand. The determinant of this matrix will be equal to the determinant of this matrix plus the determinant of this matrix. It's because when you expand terms, no, you have the C1 plus C2 means D1, C2 plus D2. All that will split, and then you'll get the determinant of this plus the determinant of this. So this is easy to check.
Ma'am,
Yeah.
if we split, I mean, every column once, and then at the in the right hand side, we will.
You can repeatedly
as
do
it
this,
is.
right?
Okay.
Yeah, if you have some variation in the second column as well, you can keep that fixed for the moment here and then split, and then you can do split again for that column and all that. Right?
Ma'am,
This is
one
what you're
small
saying,
follow
right?
up down. Ma'am,
Yes.
if in the second, like let us say in the third column, it is a addition of two elements. But if it is in the second, like in the B1 plus.
Anything. I just chose the last column because there was place to write. That's it.
Ma'am, how does it look like? Like if A1, B1 plus D1, then C1 is there. So in that case,
Say suppose C1 plus E1 is also there.
okay.
This is not only
Yes.
for 3 cross 3. This is for anything, any order.
Ma'am, so
This
this
is what?
property which you are showing, this is always true, but the determinant of a plus b may or may not be true sometimes.
This
Can we
is
say that?
this is not true. Determinant of a plus b is not equal to determinant
Not
of a
equal
plus
to, right.
determinant. And what I have written down is not that.
This is different, right? But and this is always true.
Yeah.
This is always true.
What I've
Split-
written down now is always true.
Splitting is always true, but not the determinants. Is that right? Oh.
Yes. So this is what? You
A1.
can do the same thing. You can fix the first and second columns
Split the third
and
one.
then split the third column.
So no need to split the second one. You mean to say?
You can do that in the next step. That's what I'm saying.
Okay. Okay.
Yeah. So A1, B1 plus D1, E1. So it'll be like this. And then here now you can split. So this is A1, B1, C1 plus A1, D1, C1 plus here I'll get 2 more matrices, right?
Okay. 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 Thank you.
So now using this property, what I was telling is, let me jump.
And ma'am, can we see the property again? I mean, I was just noting it down. So
Yeah. 1 second. So the property is this.
अम्मी यार पानी भर दो प्लीज.
Okay, this can be for any column. I'm just putting it for the third column. Is the property clear?
Yes, ma'am.
Yes, ma'am.
Here, keep in mind that we are not adding the 2 matrices here. Means this is a different matrix, this is a different matrix, and this matrix is not the sum of these 2 matrices. And vertical lines denote determinant. So it's something like this. Determinant of C1, C2, C3 plus C4. If I have the columns something like this, it's going to be equal to determinant of C1, C2, C3 plus determinant of C1, C2, C4, right? Where C1, C2, C3, C4 and all represent some vectors.
Ma'am, then vector additions, in that case it is equal, but in the upper one, which you have shown that as addition of 2 blocks, that is correct also, right?
Which one?
Ma'am, this A1, B1, C plus C1, B1, this is correct. This holds true for every irrespective of any column it is. And second line which you have written, the determinant of these 3 columns also equal to determinant of these vectors. C1.
This is not a vector. C1 is itself a vector. You cannot find the determinant of rectangular matrix, no? It's a square matrix. C1, C2 are all vectors.
Ma'am, what exactly it means? Like determinant of C1, C2, C3 means determinant of this.
You take the first column, represent this as C1, represent this as C2,
Okay.
column 1, column 2, say this is C3. Oh, okay, there's a C here and here. Okay, fine. This is column 4 or something like that. I'm just representing each column as a vector and writing it down in the short form like this.
Okay.
now, can we take a numerical example?
Yeah, we will. And the same thing you can do for rows as well. Instead of adding D1, D2, D3 here, if it was added to the rows, even then you could have split. How would that be? A1 plus D1, B1 plus Okay, let's write it like this. B1 plus A1, B1, C1, A2 plus D2, B2, C2, A3 plus D3, B3, C3. This is A1, A2, A3, B1, B2, B3 plus D1, D2, D3, B1, B2. Is it clear?
Yes, ma'am.
Yes, ma'am.
Why should this be true? Why can I do it with rows as well?
Because determinant of a transpose is same as the
Yeah, exactly. Determinant
determinant.
of A is equal to determinant of A transpose. So if I want to do it for the rows, I can just take the transpose of the matrix, convert it into columns, and I already know for columns, right?
Yes, ma'am.
Okay. So there was one problem, no? Where when we do this operation, this is exactly what is happening. R1 plus some alpha times R2. So say I have 1, 2, 3, or A, B, C, D. What is my new matrix now? So when I do this operation, my determinant does not change, right?
Yes, ma'am.
Does not change. Okay. So what is happening here? A plus alpha C, B plus alpha D, C, D. This is what I have, right?
Yes,
Right.
Yes.
So the determinant of this matrix is going to be determinant of A, B, C, D plus determinant of alpha C, alpha D, C, D by the above property, right?
Yes, ma'am.
Yes, ma'am.
And this is 0 because
Yes,
one
ma'am.
row is a scalar multiple of the other.
Yes, ma'am.
So the determinant remains the same. Is it clear?
Ma'am, I have a confusion between A inverse and A transpose. Could you explain?
A inverse.
A inverse and A transpose.
Okay. A transpose is nothing but interchanging the rows and columns. A, B, C, D transpose is you write the rows as columns. A, B becomes the first column. C, D becomes the second column. This is transpose. Inverse is a big procedure.
Hello, madam.
Yes.
Sorry, ma'am, I have joined late. Madam, you have just written that A plus alpha C, B plus alpha DT. When you have split into two determinants, is it not equal to like determinant A plus B is equal to determinant of A plus determinant of B?
No. I'll
Why, madam?
suggest you watch the first 15 minutes of the video later. This has nothing to do with what's going to happen after this.
Okay.
Yeah. Because I have to explain everything again. So
Okay, madam.
you can maybe watch it later. This has nothing to do with what we are going to do. Okay.
Ma'am, A inverse also, madam. A inverse.
Yeah, A inverse we will do. We will do in the discussion. Okay. So yeah, this was all week 1 content. And then we had also seen what a minor and cofactor was and how the determinant is related to the minor and cofactor. But yeah, in week 2, yeah, we'll just start week 2 content and we'll quickly recall what a minor is, what a cofactor is, and how to find the determinant using minor and cofactor. Okay. So what is a minor?
Minor is supposing we take A as a minor, then we will eliminate the ith row and jth column, and whatever the matrix we have, then we will take this take that determinant.
Yeah. So whatever is the minor of whichever entry of the matrix you want to find out. Suppose you want to find the minor of the Aijth entry, you eliminate the ith row and jth column, and then whatever is remaining, whatever is left out, you take the determinant of that matrix. So if I want to find out the minor of A11, I will eliminate the first row, first column. This is the left out portion of the matrix. I find the determinant of this submatrix, and whatever answer I get, that is the minor of A11, right?
Yes.
Yes.
And it's denoted by M11, minor of A11. And what is cofactor?
We will multiply -1 to the power I plus j.
I plus
We multiply -1 to the power I plus j.
Minus 1 power I plus j into minor of Aij. Yeah. So here it's 1, 1. So I will multiply minus 1 power 1 plus 1 here. So for this reason, the cofactor will be of the same sign for those entries whose index add up to even numbers. Yeah. For all these entries, the sign of the cofactor will be the same as the sign of the minor. For the other 4 entries, the minor sign will be reversed when we have to calculate the cofactor, right?
Yes, ma'am.
Yes.
Yeah. And the determinant of a matrix is nothing but take any row or any column, and then you take all the entries in that row. So AI1 into CI1 plus AI2 into CI2 plus AI3 into CI3. You multiply each element with its cofactor and do this for all the elements of the row or column that you want to expand along. So this is the general formula for the determinant. So we can do this along any row or any column. So we will just, the easiest way to expand will be pick the row or column with maximum number of zeros, right? So that computation becomes much simpler.
Can you repeat cofactor once more, please?
Yeah, so you know what a minor is?
Yeah.
Yeah. So for the cofactor, you just multiply the minor with minus 1 power I plus j, where I denotes the ith row. The element belongs to the ith row and the jth column. So you multiply by minus 1 power I plus j. That's it.
Okay.
Yeah. Okay. Mm.
And how do we calculate the determinant using the cofactor matrix? The last you have mentioned.
No, the inverse is you cofactor matrix is something different. Are you asking about the inverse or the determinant?
In this block, in the square block, you have written.
Yeah. So this is, I'm expanding along the ith row. So when I expand along the ith row, my first element is AI1, right?
Right.
In my ith row. So it's going to be AI1, AI1, AI2, etc. AIN. So along this row, when I want to expand, I will multiply each element with its cofactor. So AI1 with the cofactor of AI1 plus AI2 into the cofactor of AI2. Got it?
Yes, I got it.
Yeah. Okay. So this is the general way of finding the determinant. So I guess there is a matrix here. Yeah. So what is this? Find out M23. This is a 3 cross 3 matrix. How should we find out M23? That is the minor of A23. First of all, what is A23? Entry. Yeah. So how are we going to find the minor of that entry?
Third column to the first row to the
second
Yeah, you eliminate the row and the column where it appears, and then whatever is remaining, you take that submatrix. The remaining one is this. You calculate the determinant of this. So that's what? Minus 1 into 0.
2
minus 2 into minus 1. So it's 2. So what will be the cofactor of this entry?
This is also 2.
Minus 2.
Minus 2, ma'am.
Minus 2.
Okay, yeah.
Minus 1 raised to
Cofactor
5.
of 2, 3 will be minus 1 power 2 plus 3 into minor of A23. So minus 2. Okay. How am I going to find the determinant? Yes.
Determinant also.
Minor is the
Minus
submatrix
2.
or the determinant of
Determinant
submatrix?
of the submatrix. It's the determinant of the submatrix.
Okay.
It's a number. Minor is a number.
Determinant is
Ma'am,
minus
minor of A23 is also -2.
No, it's 2, no? We calculated it's 2.
Yeah, it is 2, ma'am.
The minor is 2. The cofactor
Determinant
is
is
-2.
-2.
The
and
determinant of
Ma'am,
this matrix is what? -1 into
ma'am,
0.
then we multiply
Minus.
-2 plus 2 into -1 here. So here minus.
No. Minus, no? How do you find the determinant of a 2 cross 2 matrix? AD
minus CB.
BC.
BC.
So there'll be a minus sign here.
Yeah.
Is it clear?
Yes, ma'am.
Oh.
Ma'am, you will be uploading this document, this PDF?
Yes. Did you get the previous
Yes.
Yes,
live
Yes,
session?
ma'am. Yes, ma'am. We
I
got it.
got the previous one.
Yeah. Okay. So how will we find the determinant of this matrix? Let's expand along the second row because I already know the cofactor of an element in the second row.
And we can also expand along the second column because it will be easier.
Okay, fine.
It will be easier.
Easiest when we expand along the second column. Okay, we'll do both. We'll expand along second row as well as second column. In both the cases, I should get the same answer, right?
Yes, ma'am.
Yes.
Okay. So let's expand along the second column first. How am I going to do that?
2 into
2 into, okay, let me write the entry. A12 into cofactor A12 plus, okay, I'll write it as C. C12 plus A22 into C22
C22 plus
A23.
A23 into C23.
Yeah. So A22 is 0, A23 is 0,
A23 is 0.
and
Only
A12 is 2.
A12.
So it's going to be 2 times C12.
Yes.
And what is C12?
Minus 1 to the power 3 into the
Determinant
minor
of determinant.
2 minus 1 minus 1 1 determinant.
Yes, ma'am.
2 minus 1 minus 1 1. So that's 2 minus 1 1 minus 2.
Ma'am,
Right?
that would be A32. A32.
Ma'am, you began.
A12, C12, A22, A32.
Oh, okay, fine. 3 2. 3 2. Thank you.
Ma'am, you began with A1 to C2, 1 to. Can you just tell that? I could not.
I was expanding along the second column.
Okay.
Yeah. Now suppose we do it along the second row. In this case, it would be A21 C21 plus A22 C22 plus A23 C23. Second row. So this is 0. A23 C23. A23 is minus 1. C23 we already, we calculated C32. Okay, fine. Then let's do it again. So what is A21 is 2. So 2 into, what is the cofactor of C21? Means
2001
minus 1 power 2 plus 1 into determinant of
2001.
No, second row first entry. Minus 1
-1
0
0 -1 1.
minus 1 1.
No,
Plus-
ma'am, it's 2 1.
No, ma'am.
A2.
It's
Ma'am, it's 2001.
Ma'am, first.
A21. Oh, okay. Sorry. This
First
row,
row.
this column.
Yeah.
Okay.
2001.
2001. Okay. And then A23 is minus 1 plus C23 minus 1 power 2 plus 3 into determinant of 2 3 minus 1 2 minus 1 0. So that's 2 into minus 1 into 2 minus 1, minus 1, 2, right?
Yes.
Minus 1 plus 2. So this is minus 4 plus 2 minus 2. So you expand along any row or any column, the determinant will be the same. Then okay. What is the cofactor matrix? What is the cofactor matrix?
Minor with sign.
The cofactor matrix is the matrix whose entries are the cofactors of each entry of the matrix, right?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yeah. So, okay, let's take a simple example, 2 cross 2. In the 2 cross 2 case, what is the cofactor of this entry?
4.
4.
Yeah. So it's going to be minus 1 power 1 plus 1 into this entry. Yeah. So this is C11. So my cofactor matrix will be 4 and then
Minus 3.
Minus 3.
Minus 3.
Minus 3.
Minus 2.
Minus 2.
Minus 2. 1.
1.
Yeah. For 2 cross 2, it's easy, right? You just interchange the diagonal entries. And then for the off diagonal entries, you change the sign and interchange the off diagonal entries. What is the adjoint of a matrix?
Then adjoint is same as adjugate of the matrix.
Transpose of cofactor
Yeah.
elements.
So transpose.
The transpose of the conjugate cofactor matrix. It's denoted by ADJ of A. So you just take the.
This is also adjugate also, or like adjugate also.
You just take the transpose of the cofactor matrix, you get the adjoint. So here the adjoint is 4 minus 3 minus 2, 1.
Ma'am, can you just repeat what you said for cofactor matrix for 2 cross 2? Means you just have to change what? The sign.
You interchange the diagonal entries. For the diagonal entries, diagonal positions, you just interchange their positions. Yes. For the off diagonal entries, you interchange their position and change the sign as well.
Okay.
I mean, is this valid for 3 cross 3 matrix as well?
No. This is only for 2 cross 2.
What about
it's
3 cross 3
because the
matrix?
minors, if the minor of this entry is the other diagonal entry, right?
Yeah. Yes, ma'am.
For that reason, this interchange thing works. But in 3 cross 3, it doesn't work that way, right?
So what about 3 cross 3 matrix?
No, there you have to
need to find.
Yeah, you have to find out the cofactor of each entry and then fill it up.
Excuse me, ma'am.
Find the minor, then the cofactor, and then write down that.
Yeah.
Hello.
Yeah.
Ma'am, actually I lost when you were explaining adjoint matrix.
Okay. The adjoint matrix is nothing but the transpose of the cofactor matrix. That's it.
And will you take the problems from the practice assignments in today's section?
Yes. Whatever we are discussing, whatever concepts we are discussing, all problems related to that we'll do.
Okay.
I have lots of
Ma'am,
can you make it quick?
Ma'am, can we see activity question?
Okay. So till adjoint, whatever we have discussed, for corresponding to that, we will see some problems.
And problem activity 2.1, question number 4.
Ma'am, could you just go back to what you've just written?
Okay. We'll do activity before that.
2.1, question 4.
Ma'am, can we discuss 3 cross 3 cofactor matrix, one example, please?
Yeah, sure.
Okay.
So
We've just transposed CT, right?
yeah.
Sorry, C. We've just transposed C.
The cofactor matrix. Yeah.
Thank you.
This is valid for only 2 cross 2.
Yeah,
So
that
this is
interchange
not
thing is
valid
valid
for
only for.
interchange thing is valid only.
Okay. So what is the cofactor matrix for this matrix?
I understand cofactor for
That is for create
one
in this
first
case.
entry, that is
First
1.
entry is 0.
It is 0, 0, 1, 0.
Huh.
Ma'am,
So you
that is
find the
suppose,
cofactor of this entry, put
Yes,
that
ma'am.
here.
first write the minor matrix.
Yes, ma'am.
Let us write the minor matrix and then in the end change the sign.
Okay, I have to evaluate.
Yeah.
I have to evaluate the cofactor matrix of
Yes.
and
Of
then
each
put it
entry,
there
you evaluate the cofactor and then put it as a matrix. That's it.
in the same position.
Yeah.
Corresponding to that.
Okay, ma'am, got it.
So if I want to find for this entry, it's going to be a 0 again. For this entry, it's going to be 4. So you just corresponding to each entry, you put the cofactors there.
Yes, ma'am, got it. Got it, ma'am.
Yeah. Okay.
Thank you, ma'am.
Before going to activity, we will do this problem. Yeah. There was an error in the portal, right? One of the options was right, but it wasn't showing on the portal.
Ma'am, I want to make a request.
Huh?
I want to make a
Third
request.
option, ma'am. Right.
I have lots of doubts in the how the determinant is related to the solution of the equation, system of equations.
Okay.
And
yeah,
all such questions are my doubts, and I want to discuss them. So
yeah,
can
we
you please
will
make
get to that. Once we start Crammers Rule, we will discuss that.
Okay.
You just discussed adjoint matrix, right? And you said it will be the transpose of a matrix C.
Yeah.
So it has nothing to do with the 2 cross 2 or 2 cross 2. It's a generalized statement.
Yes.
It will always be
So
transpose
the adjoint of this matrix, if this is A, its first column will be 0, 0, 4.
So I have to write the transpose of cofactor matrix, right?
Yes.
Only then it will be adjoint matrix. Got it, ma'am. Thank you.
Yeah.
Okay.
In
Is
this
this the
problem,
only way we can find
I asked,
adjoint of any matrix?
Ma'am, I asked this because you just wrote that adjoint matrix will be adjoint of A. However, A was 1, 2, 3, 4, and the cofactor matrix was 4 minus 3 minus 2, 1 in 2 cross 2 matrix. That's why the confusion
yeah, you find the
arose.
cofactor matrix and then take
transpose of the cofactor matrix, right?
Yeah.
Yes, ma'am. Got it.
There was someone else asking a doubt, right? What was it?
Yes, ma'am. I was saying that is this the only way we can find the adjoint of any matrix?
Yes. This is the only way. For a 2 cross 2 case, it's simple.
Yeah. That is just a observation.
Yeah, you interchange the diagonal entries.
Yeah.
To get the adjoint matrix, you just change the sign of the diagonal entries, right?
Yeah, but it's not a very big trick. It's just an observation, right?
Yeah.
Thank you.
Okay. Yeah, so let's finish this problem.
I have a question.
So,
like, what is the significance of these cofactor and minor?
Yeah, using this, we will find the inverse of a matrix. And the inverse has a lot of applications, right? You find solutions to systems of linear equations using inverse, right?
Yes, ma'am.
Yeah.
All right.
Okay.
Like
so what is the relation between A and B here? Is there a question?
It's a tool, like, there means to arrive at the inverse of the matrix.
Yeah.
Okay, thank you.
Okay. So what is happening in A and B here?
One row of the 2 rows of B have been interchanged, which makes it A.
Yeah. So the first and the second rows have been interchanged. And because of that, what will be the effect on the determinant?
It will bear a minus sign.
Minus sign. Yeah. So this is wrong. And then what's happening in B and C?
The first row has been doubled.
Yeah. So the first row is becoming 2 times. So in that case, what will the effect be?
So determinant will be twice of that of B.
Twice of that.
Twice of B.
Determinant of C will be 2 times determinant of B.
Not minus 2, right?
Yeah, it's not -2, so this is right. I guess in the portal this was not correct.
Yeah, there was some issue in the portal regarding this question.
So, ma'am, is this the appropriate option? Because there could be many things which
Yes.
are not equal, and it happens to be one of them.
Yeah, but that's why you're given options, right? You pick from those.
Okay, ma'am.
Could you repeat the last thing? How is determinant of C equal to
2 times determinant of B, because the first row of B is multiplied by 2 to get the first row of C.
Okay, so the negative would not be there.
Yeah, so it's not equal to -2 times, it's in fact equal to 2 times.
Had it been the row would have been changed and then it would have been doubled, then it would have been a negative sign, right?
Yeah, from A to C, it's a -2 times, right?
Det of C it should be equal to -2 det of A.
Yeah.
Yeah, as
the
it is
fourth
mentioned in the D option.
Right.
Yeah.
So, ma'am, could I just confirm one thing? Ma'am, so if there's one row, elementary row operation change, it will be minus. And then if it's...
No, it depends on what the elementary row operation is. Row interchange, yeah. For interchange, there'll be one minus, yes.
Okay, so if there are two row interchanges, then minus becomes plus, right?
Plus, yes.
Okay, and otherwise, if there's some operation like 2 times, then it will be
Determinant will get twice.
Okay. Okay.
What is
just
the
twice.
determinant of 4032, 4034, 4044, and then 4026, 4028, 4030, and then 2019, 2020, 2021. What is the determinant?
4
4
times
times 0.
4 into 2 square. 4 times.
There's a 2x here, 2x here. So 4 into determinant of
B.
Which is also equal to, no,
Zero.
not A, B.
A.
Yeah, because in A, there is an interchange of row. Means from A, there's an interchange of row.
So for
it's
four,
going to
for
be
minus 4
-4.
times
Yeah.
determinant of
Determinant of A, yes.
Yeah.
Okay.
Okay, so we'll take activity questions. 2.1.
So,
Ma'am, just one.
activity 5, question 3.
Ma'am, can you please
yes.
go back to the question, please? Where you made it -2. Can you please go back to the page? Yes, please go on.
Yes,
Ma'am, यहाँ पे like it is minus not equal to -2 guys. Okay. So it is true only.
It's actually equal to 2 times determinant of B.
Yeah, so it is true only, right? This statement is true.
Yeah.
Ma'am, I have a question here. Ma'am, can you hear me?
Yes.
Yeah, option 4, the determinant of C should be 2 times the determinant of A, right?
No, there is a row sign, row interchange here, no? So there is a minus sign. From A to C, what is happening?
Yeah. Oh,
A
yeah,
to
fine.
C.
That's correct. Yeah, got it. But we have our multiple of 2 in C. So,
Yeah.
2 times determinant of C is equal to minus determinant of A, right?
No.
Because 2 is a
Determinant
multiple
of C is 2 times determinant of, let me write it down. Determinant
No, because
of,
2 is a multiple of determinant C, right?
no, you pull the 2 out from this first row.
Yeah, I got it. But then you have to multiply, C is equal to 2 into determinant of C is equal to minus
No.
determinant
Once you
of
pull
A.
out the 2, you don't have C on this side, no? You have some other matrix.
It will be a changed matrix. It will not remain C again.
Okay, got it, ma'am.
Once you take the 2 out, yeah.
Once the 2 is taken out, it becomes a matrix A. Kindly note.
It becomes B, in fact.
It
and
becomes
then
B,
the
in fact.
interchange. Yeah.
And the B is already, B has already got interchanged rows. That's why there was a minus sign already. So it's a
Got
kind of
confused.
comparison and not an equation. If you can
Yeah.
please see.
Yeah.
Thank you.
Okay. AQ 2.1. Yeah, go ahead. Anyone.
Okay. Activity 5, question 3.
And question 2.1, question number 2. And question number 2.
Okay.
Yes, ma'am. Why third option is not correct? And why fourth option is correct?
You tell me.
Okay, ma'am. And see, P multiplied by A multiplied by P inverse. When we multiply P and P inverse, we get identity matrix, right?
Yeah. D is P A P inverse.
And P into P inverse
So,
is identity matrix, and identity matrix into matrix A is equal to matrix A. So D is
are you
equal to
telling
matrix A.
P inverse A? So this is A?
Yes, ma'am.
No, but how do you know that A and P inverse commute? How can you tell A P inverse is equal to P inverse A? Matrix multiplication is not commutative, no?
Yes.
Okay.
But what do we know? Once we take the determinant, what is determinant of P A P inverse?
Determinant of A.
Determinant of A.
It's determinant of P into determinant of A
Determinant of A
into determinant of P
determinant of
inverse.
A inverse.
And what is the determinant of P inverse?
1 by
determinant of
P.
Yeah, so that gets cancelled.
upon
You'll
it.
get determinant of A.
Determinant of A.
Okay, we still haven't discussed inverse. We'll just write down the formula for the inverse here. So A inverse is nothing but 1 by determinant of A into adjoint of A. Right?
Yes.
Yes, ma'am.
So you can, A inverse is possible only when determinant of A is not equal to 0, because I'm dividing by determinant of A. So when determinant of A is not equal to 0, you call A is invertible.
Yes.
Or non-singular.
And what is the meaning of non-singular?
It's not singular. By singular, you mean determinant is equal to 0.
Okay, by singular we mean that it is null matrix kind of thing.
Not null matrix. Null matrix means it's a zero matrix.
It's not
but,
a singular matrix, is it?
The determinant is 0.
The singular matrix is the matrix which has a determinant equal to 0, right?
Yeah, it's a matrix whose determinant is 0. So a matrix whose determinant is non-zero is said to be non-singular. That's it. Okay, so
Madam?
whoever asked this doubt of why P is not equal to or A is not equal to D, can you give an example where they are not equal but still this is satisfied?
Can you please repeat?
Whoever asked the doubt should give.
Yes, ma'am. I asked the doubt. What was the question?
So the question is, can you, so now you agree that option
Yes, ma'am.
3 may not be true, right?
Yes, ma'am. I got it, ma'am.
So can you give an example? Like we still haven't shown that option 3 is not true.
Okay.
Okay, maybe you can try this out. Oh.
It's a 3x3 matrix.
No, this is a 2x2. I am taking an example of a 2x2 because I can easily construct one. Ignore my workings. You will study all this in MLF. What am I doing? I'm trying to construct the matrix.
Can't we just put any random matrix in center? In place of P, we'll put something, and in the other side we can just put adjoint of A by determinant of A. Something simple.
If we
Just
take
to
a
give an
3 cross
example.
3 matrix and if we take 3 cross 3 matrix and interchange its two rows, the matrix would be different, but the determinant would be same.
What can you repeat? In the place of A, put?
Suppose we have a 3 cross 3 matrix.
Right?
A matrix is a 3 cross 3 matrix, and B matrix we get by interchanging two rows. Shift row 2 and 3 to top position and 1 to the last position. So the matrices are different, but the determinants are same.
No. But this has to be satisfied. No. That's what I'm trying to do.
What I was telling was in the place of A, let's put any random matrix. Initially, we can just put another 2 cross 2, and in place of P inverse. Anyways, it's easy to find the inverse, right?
Okay.
Yeah. Okay. If you do that, it's hard to find D. Okay, my bad.
Actually, any A will not work. That is the thing. A should be diagonalizable, which is something you will study in MLF. Yeah. What am I trying to do? Okay, fine. This works. And then this.
Can we do it taking an example? What I was trying to say, suppose our matrix is 1, 2, 3. In the second row, 4, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right?
Okay. No, it's not going to be easy for a 3 cross 3.
No. I want to just tell you that regarding matrix D and A. Right? The question is that matrix need not be same, but the determinants can be same.
Yeah. That is true. No, that has been shown here. No, but the DNA has to satisfy this property, right? That D has to be equal to PA P inverse. It cannot be any random DNA.
Yes, I got that point. But what we were talking about this option. The matrix A must be equal to B. So this is not. This was the question.
Yeah, that's not true. Because no, you cannot again take any random A and D. It should satisfy this condition.
It would satisfy them, I suppose.
What is P and P inverse that you will take? Means what will P be there?
Okay.
Oh, it's asking for a 3 cross 3. Okay, fine. As long as you agree that D and A may not be equal, it's done. Why am I not able to construct this matrix? X1, X2. X1 plus X2 is 2 times X1, 0, 2X2 is... Oh, 2X2 is 2X2. Okay, fine. So... Okay, X2 can be anything.
Verify it.
And minus X1 plus X2. X2 should... Oh, 1, 1. This would work. You can check if this is P, this is A, and you calculate the inverse P inverse, then I'm going to get this D. So you can see that A is not equal to D, but we already know that determinant of A has to be equal to determinant of D.
Is there a generalized solution for this, or just we have to find an example out of the blue?
No, the thing is, if A is a diagonalizable matrix, then you can write it like this, where D is a diagonal matrix. So the matrix A need not be diagonalizable. So all this you will study when you study eigenvalues and eigenvectors. So this question is just to sow a seed for that.
Excuse me, ma'am.
Hello, ma'am.
Yeah.
Hello.
Here,
Yes.
P into P inverse is equal to 1 identity matrix, no, madam. P cross P inverse is equal to identity matrix, and A into identity matrix is equal to A. Can we say that here?
No, you can say that when you know that PA is equal to AP. Only then you can interchange, no? PA, AP. Otherwise, you cannot do this.
But P into P inverse is equal to identity matrix. Is it
Yes,
not?
yes.
madam?
But you,
AP inverse is identity.
but you
Agree.
cannot multiply P and P inverse. That is the question. That is the matter.
He
You
has
cannot
already
multiply.
crossed that. See the regal line and she has put a cross on it.
Yeah.
This is not true. P into A into P inverse is not equal to P into P inverse is A.
That's because AB need not be equal to BA always.
Yeah.
I have one relevant doubt in question number 9 of the 2.1.
Okay.
Question number 9, option number 2.
Question number 8 also, madam. I have.
This we discussed last week, no?
Yeah. Question number 8, I think option is wrong here given.
1 and 2 is right. A1
Right,
and
but
A2.
Yes, sir, they are right.
But
They are
option
right.
is showing other, madam. A3 and A4.
No, it has been updated.
Okay.
Yeah, it has been updated. Okay. Question
Ma'am,
number 9. What is the doubt?
Option number 2. Right. I got it. Determinant of A4 is equal to, should it not be equal to A times determinant of A?
8
I'm
times
somewhat
or 8
confused
times?
in this
Oh, 8.
option.
No, no. See, this is the matrix, right? C1, C2,
Yes,
C2, C3.
it is C1, C2, C3, and then addition of 2 matrices.
Yeah. C1 plus C2, C2 plus C3, C3 plus C1. The determinant of this matrix is going to be equal to the determinant of C1, C2 plus C3, C3 plus C1 plus determinant of C2, C2 plus C3, C3 plus C1. Agreed by that property that I mentioned?
Yes. Agree.
So I can split it this into 2, this into 2, this into 2, this into 2, right?
Right.
So I'll get determinant of C1, C2, C3 plus determinant of C1, C2, C1 plus determinant of C1, C3, C3 plus determinant of C1, C3, C1 plus 4 more matrices from the second matrix, right?
Right.
This is 0, right?
Why
2
zero?
columns are C.
2 columns.
Yes.
Yeah.
Okay, yes, sir. This is 0. That's also 0.
This is 0. This is also 0. So similarly, out of the 4 matrices here, you will get 1 matrix which survives.
Okay.
You can expand this and see which one survives. C2,
Okay,
C2,
got it.
C3 will be gone. C2, C2, C1 will be gone. C2, C3, C3 will be gone. Only C2, C3, C1 will remain. But this is not the matrix A. But the determinants will be the same because you have done 2 interchanges of columns, right?
Yeah.
Yes, ma'am. Yes, ma'am. Got it.
Yeah.
Okay. I didn't get means it was too fast for me.
I have a submission here. This property was not discussed in the lectures, right?
No, this is something you can observe, no? Means it's not a property as such. You can expand and check that.
Okay.
Yeah, it's kind of calculation part.
Yeah. Yeah. So someone hadn't got it. Is this step clear?
No, I'm actually expanding. Means I was too slow to expand when you went ahead, so I got confused in the middle. So that was.
So now is it clear, or do you want me to explain?
I just need a minute, please.
Okay. Okay, there was someone else with a doubt. Maybe we'll take that down.
Ma'am, can I ask my doubt?
Yeah.
Ma'am, activity question 2.3, last question.
We haven't come to 2.3 yet, right? What is 2.3? Okay. Anyway, last question.
Yeah, I have, so we have to find out the correct options. I have solved the other
Yes,
options, but
can you please discuss question number 9 and this one also? Question number 9 also.
Okay. This one. You have what and
yeah,
all
I
have you
was
solved?
saying before someone, okay, so I was saying that I deduced the other answers, but the last option is also correct. That I'm not able to deduce how to come to the conclusion how it is correct.
It's a 2 cross 2 matrix, no? You can in general find the inverse, find the adjoint, and
Yeah,
find.
I tried that, but the adjugate of A, the inverse of that, the second part, right? The right hand side, I'm not able to get how to get and arrive at that term actually.
You have to find
Actually,
the
I
adjoint of the matrix, and you should take the inverse of that matrix.
Ma'am, I want
Yes,
to
ma'am,
discuss
I
about the
tried that.
approach of
Actually,
first
that's what
question.
I'm not able to. So if you could help me to
There's someone
solve.
else telling something.
One
What
thing
is
more,
it?
ma'am. One thing more. I want to know how to approach such questions. Should we take an arbitrary matrix, say 1, 2, 3, and 4, and calculate all these options and then mark the right name?
No, you shouldn't take 1, 2, 3, 4. This is a question for any 2 cross 2 matrix. So you should take A, B, C, D. Yeah, the hint is given, right? Take A, B, C, D.
Yes, okay, ma'am. I got it. But do we have to calculate each and every option, like adjoint of
Yeah,
B, adjoint of A?
there's no other way, no? Yeah, there's no relation between the
Okay.
options, no? So you have to calculate all of them.
Okay.
Okay. Before starting
And question number
Crammers
9.
Rule. Yeah, we'll do that. So A, B, C, D. What is the adjoint?
Adjoint, we can just switch the diagonal like D minus C,
D
then minus B, D. A.
Yeah. What is the inverse?
Inverse would be 1
adjoint.
by determinant of A.
1 by determinant of A.
Yeah, then multiplied by this adjugate.
Adjoint.
Okay. So this is A inverse. What is the adjoint of A inverse?
This is the part that I got lost actually.
Yeah. So you have to flip the diagonal entries, and then you have to change the sign of the other 2 entries, right?
Yes.
So it will again become the original matrix.
So this is A. And then what is adjoint of A inverse? Adjoint of A is this. So what is the determinant of the adjoint?
This is where I got stuck, ma'am.
What is the determinant of this matrix?
DA minus BC.
DA minus CB.
This 1 by AD minus BC, this is just a constant, right? And we are taking the adjoint of the matrix.
Yeah. And then you take the inverse of this matrix. So you flip the diagonal entries, change the sign of the off diagonal entries. These two are the same, right?
Thank you, ma'am.
Does that make any difference? AD minus BC and DA minus CB, they both are the
No,
same?
they are all numbers, right?
Right,
They're all
right.
numbers. So you can multiply A into D or D into A. Doesn't matter.
Ma'am,
Ninth question.
ma'am, activity 2.
Can you repeat activity
2.4?
Okay.
Question 2.
I don't think we should do echelon form today. Can we do it in tomorrow's discussion?
Yes, ma'am.
Actually, I was confused about how do we get infinite solutions, unique solution, and no solution using the echelon form.
We will discuss that in tomorrow's
the questions related to those, like 2.6, question number 5, 6, 7, 9. I'm a bit confused in this topic, man. To find the solutions of system of equations using various methods.
So echelon form and the Gaussian
Especially when-
elimination will be discussed in detail in tomorrow's session.
Okay, I was about to ask about this.
Okay. Is the ninth question clear now?
Yeah,
Like
yeah.
someone had asked for the ninth. Yeah.
No, madam, please do that.
Oh, no? You do the same. You have an upper triangular matrix A, B,
Okay.
0, D.
Okay.
And then you do the same. You find the inverse, adjoint.
Okay,
What is the
madam.
determinant of this matrix?
AD minus 0. AD.
Yeah.
Only AD.
So when you have an upper triangular matrix, the determinant is just the product of the diagonal entries.
Of the diagonals. Okay, madam.
So you can do the same for whatever we did for A, B, C, D. You just have C is equal to 0 now. That's it.
Okay.
Okay. And oh yeah, so we have covered lecture 3, I guess. We have discussed all this. Okay, let's do Crammers rule and then come back to activity questions.
So we are discussing till 2.3 today.
Yeah. You have a session at 8, right?
Yes, ma'am. Yes, ma'am.
Stat 2 session is there at 8 p.m.
Yeah, that's why I split it like echelon form in tomorrow's session.
That would be good, ma'am, because in one session, if we cover everything, even for us, it would be confusing.
Yes,
Yeah.
ma'am. Absolutely. I don't even finished the last lectures, so it's okay now.
Yeah. And then
Yes,
on
ma'am.
Tuesday, maybe it will
Excuse
be
me?
like completely all doubts and solve it. Yeah.
There was a thing actually. This might not be a right session to bring it up, but tomorrow actually this session as well as machine learning foundation, they have been coinciding. Not sure. Like I've dropped a message and we were told just to go to recording session, but it's not an ideal situation for
But
us.
how are
So
you doing MLF and maths too? Isn't maths too
Ma'am,
a
he must be
prerequisite for
diploma
MLF?
student.
yeah, I'm a direct entry diploma student.
Oh.
You can do one
Yeah,
thing
so-
that you can watch a recording afterwards.
Yeah, that's what I have been doing. Like either going with recording of this or that. So I was just wanted to know
Because
like.
there are many sessions, so it coincides.
So is it?
Yeah, it's
So I just had
mostly
it with one
split in
session.
such a way that no two foundation sessions, foundation course sessions
Yeah.
overlap, and no two
Yeah, but
diploma
for
sessions.
diploma guys, that happens.
Sessions have been arranged according to the degree program students. Convenience, I
Yeah.
guess.
But foundational level courses sessions are overlapping. I think today we
No, they
have.
don't overlap. It's because one session goes longer than
Yeah.
the allotted time. That is why they overlap, right?
No, ma'am. Today, I mean tonight from 8 p.m. We have CT session and start 2. I think.
Okay, again, it's split into like the first 4 and the second 4 kind
Yeah,
of. So CT is supposed to be in the first 4.
Term one thing and term.
Ma'am, just
Yeah.
one thing to add. Tomorrow we have a session at 2. So
Yeah.
would you be continuing the same tomorrow?
Yeah, so I might not be taking the session. Whoever is taking will continue from here,
Okay, fine.
from whatever I have finished.
Okay.
I have one general doubt. What
Yeah.
was this reflection assignment when it was mentioned in grading?
What is it?
Reflection
What
assignment.
was?
Reflection assignment. It was
Reflect.
related to some discourse forum that reflection assignment would be given. Where is it? I don't know, ma'am. It was mentioned on student dashboard in grading.
Yeah. In the graded assignment, you get the last question
From
based on
discourse.
discourse, right?
Yeah.
Okay. This question is mentioned as the reflection assignment question.
I don't know what it was called, but yes, if it's
No,
related
ma'am,
to
It is
discourse,
given
then it's the
separately,
last.
ma'am.
This
He's
question,
saying
last
like
question in grading
in
assignment
week 2
is
we have
from,
solved
of course,
with
from
us,
discourse
but
forum.
in week 3 there is a reflection with us.
Reflect with us. Okay, fine.
Yeah.
So reflect with us is it's a question
Kind of
that is
similar
picked
as
up
solve with us.
a graded question, and then step by step.
Ma'am,
At
not
each
reflect
stage
with
there
us.
is a question.
There is a reflection quiz.
Reflection quiz. What is that?
Yeah, that's what like it's in the dashboard
There is
now.
Okay,
There's a
okay. That
reflection
is
to
based
it.
on the discourse discussion. There is one question based on the discourse discussion.
Yeah, the last question of the graded assignment will be based on some post in discourse which was posted previous term.
Ma'am, I think this
Got
is
it.
different from the topic. We should stick to the topic. There is only 50-minute left.
Yeah, okay, fine. That was a long break, I guess. Okay. So yes.
I
Yes.
have a doubt. Activity 2.2, question number 1.
Okay, we are doing Crammers rule now, right? That is activity 2.2 will be related to Crammers rule, right? Yeah. So maybe we'll discuss the rule quickly and then go to questions.
Yeah.
Okay.
Okay. So the Crammers rule is a rule that is used to solve the system of linear equations. We already know what a system of linear equations is and all that. So how to find the solution? One of the ways is by using Crammers rule, and the rule can be applied only when the coefficient matrix is invertible. So for the coefficient matrix to be invertible, first of all, it should be a square matrix. So the number of equations should be equal to the number of variables. So you should have a square matrix, and the determinant of the square matrix should not be equal to 0. Only then you can apply the Crammers rule, and using Crammers rule, we can find the solution to the system. So how we find the solution is by doing this. So what you do is you find three different matrices which are denoted by AX1, AX2 and AX3, where X1 is the first variable, X2 is the second variable, X3 is the third variable. So how you find AX1 is you replace the column corresponding to X1 with a right hand vector. Which is the column corresponding to X1?
First column.
Yeah. So we had seen last week, right? The column corresponding to the first variable, the coefficients of the first variable will appear in the first column of the matrix, and the coefficients corresponding to the second variable will appear in the second column. So the column corresponding to X1, that is the first variable, is the first column. So AX1 is got by replacing that column by the right hand vector, which is B1, B2, B3. Similarly, you get AX2 by replacing the second column with B1, B2, B3. So now we have three different matrices, right? They are not same as A, and there is no relation between A and these matrices, right?
Yes.
Yeah. And then you calculate the determinant of each of these matrices, and the solution is given by this. X1 will be determinant of AX1 divided by determinant of A. We are allowed to divide by determinant of A because for the Crammers rule to be applicable, we mentioned initially that A should be invertible.
Can you
This is
discuss
how
this system of equations is going to have a unique solution, non-solution, and infinitely many solutions?
Yeah, that will come in the echelon form. In the Crammers rule, we have only a unique solution because the matrix is invertible. I'm going to get a particular number for each of these cases. I'm not going to get infinite solutions, and I'm also not going to get no solution case.
Pardon me,
Yes.
Can you repeat it once again?
So in the Crammers rule case, you always have a unique solution.
This is because
the determinant is not 0.
This is because determinant of phase is not 0, and the matrix is a square matrix, right?
Yeah. Only then you can apply the Crammers rule.
Okay.
And this is how you apply the Crammers rule, and you will always have a unique solution in this case. And the solution is given here. This is the solution.
Right.
Ma'am, can you please explain this one? Because taking one example, please.
Yeah.
Madam, only square matrix have non-zero. Determinant of a square matrix is non-zero.
No, we don't have the concept of determinant for a rectangular matrix, right? It's only for square matrices, determinants are
That's
different.
why we have taken only a square matrix. Okay.
Yeah. Okay. So now we have a system. X1 plus X3 is equal to 1 minus X1 plus X2 minus X3 is 1 minus X2 plus X3 is 1. So using Crammers rule, first of all, we'll check whether we can use the Crammers rule, and then we will find the solution as well. So if I represent this as a matrix AX is equal to B, what is going to be the first column of A?
1, -1, and 0.
1
Yeah.
minus 1
So
0.
you'll take the coefficients of x1 and then you will put that as the first column. 1 minus 1 0. The coefficients of x2 0 1
1
and
minus 1.
this is okay, minus 1. Yeah, minus 1. And then for x3 it is 1 minus 1
and 1.
So this is the matrix that we get. The vector of variables is x1 x2 x3 and the right hand vector is 1 1 1. So this is what we have for AX is equal to B. Now, can I apply Crammers rule? How are we going to check that?
We'll have to find the det of A.
The
If it's not equal
determinant,
to
if
0,
it
we
is
can
not
proceed.
zero, we can.
Determinant
Yeah.
of A is not equal to 0.
So I think we can expand along the first row. So when I expand along the first row, the determinant of A is going to be 1 times
2.
Determinant of this, that is 2. And then
Then
0 minus 0 times something, it doesn't matter. And then plus 1 times
1 minus 0, 1.
minus 0.
1 times
1 time.
B.
No,
Ma'am,
that is
first,
zero.
The
Oh,
first
is it?
1 into
First
0.
one
1 into
is
0, ma'am.
Okay.
1 into 0, ma'am.
Okay. So the determinant is 1. It is not equal to 0. So I can apply the Crammers rule. So by Crammers rule, how am I going to find out AX1?
Replace
Just
the
interchanging
first
in the last
column
the B matrix to
by
the
a
first
x1.
column.
The column corresponding to x1 is the first column. Remove that from the matrix and insert the B vector there. So 1, 1, 1. Everything else remains the same. 1 minus 1, 1 minus 1, 1. What is the determinant of this matrix? So if I expand along the first row.
minus 2.
1 minus 1 0 0 and then minus 1 minus 1.
That is minus 2.
Yeah. So what is my x1?
Minus 2 by 1.
1. That is minus 2.
Minus 2. So similarly, we find out AX2, AX3. Okay, let's check which option is right. AX1 is not this. Yeah, this is AX1. And AX2, what do we do for AX2?
Replace the
Replacing
second
the
column
x2
by 1 1 1.
Second column is replaced by 1 1 1. So this is not the case. AX3, yeah, right. 1 1 1 is replaced in the third column. So AX2 is not in the options. We have to find out what is AX2, find out the determinant of AX2, and then find out the value of x2. So x1 we have already calculated. Let's calculate x2. AX2. What is AX2? First column as it is, second column replaced with the right hand vector,
1
third
minus
column.
1 1.
What is the determinant? Maybe we'll expand along the third row or first column, anything. 0 times minus 2. Okay, 0, it doesn't matter. Then minus 1 times minus 1 plus 1, 0, plus 1 times 1 plus 1, 2. So what is x2?
Group upon 1, that is 1. That is 2. Sorry.
Determinant of A, 2 by 1. 2. Okay, so this
2.
is wrong. Okay, AX3 is here. We calculate its determinant and then divide by determinant of A to get x3. Is it clear how to do using Crammers rules?
Yes, ma'am. Yes, ma'am.
Determinant of A, B, like how did you get that one? Is it already given or?
No, we calculated earlier. A is here, so we calculated its determinant.
Okay.
Do we do this also? AX3 quickly.
3. So, ma'am, option 3 is
Okay,
right.
fine. Okay. And then what is it? Okay, so we can take questions on Crammers rule. There was someone with a question.
Yes,
2.2 question 2 or someone had asked.
question
right?
number 1.
Oh, 1. Okay.
I was unable to understand the last option. If determinant A is not equal to 0, then B equal to null matrix.
What is this? What is given? Okay, we have a system of equations. Matrix representation is given. B is given. If determinant of AXI is 0 for all I is equal to 1, 2, 3. Okay. So do you agree that the solution xi is determinant of AXI by determinant of A? This is 0 for all I. Agree?
Yes.
Yeah. So 0. This is a solution. Oh, okay. Determinant of A is not 0 is not given. Okay, fine. So this is a solution if determinant of A is not 0, right?
Yes.
Yeah. So if determinant of A is 0, we cannot conclude anything using Crammers rule. Okay. Now suppose determinant of A is not 0. When can you get this as the solution?
B 0.
And when determinant of A is
one row
not
completely.
So determinant of A is non-zero. A11, A12, A13, A21, A22, A23, A31, A32, A33. When this is the matrix, the determinant is not 0. But whenever you're replacing any one of the rows with a one particular vector, and that particular vector is fixed, right? What is the determinant of this matrix?
0.
0.
ma'am.
Yeah, this
Two
is
columns
0
answer.
because one is a scalar multiple of the other. But yeah, okay. So what was I going to tell? So suppose this is my B vector. AX2 is 0. Determinant of AX2 is 0. Determinant of AX3 will also be 0, right?
Ma'am?
Yeah.
Ma'am, sorry to interrupt. The second row, it is 2A31, right?
Yeah, A31.
Okay, thank you, ma'am.
So these two will be 0. But what will determinant of AX1 be?
Determinant of AX1. AX1 is also 0,
It
ma'am.
will be 2 times determinant of A, right?
Hmm.
Means, okay, if this is my B vector, if this is my B vector.
Okay.
Yeah. So the thing is, this is not happening. Yeah. For all AXI, I'm getting 0. So what do we conclude from there? Can we conclude that B has to be 0? If B is 0, obviously all the 3 determinants are 0, right?
Yes.
Yes, ma'am. It's not
But
the only
can we
case, ma'am.
conclude that that is the only possible case?
No.
I don't think so that it's
No.
the only possible case.
There can be other
Why not?
cases.
Okay, tell me this. I have AX is equal to B. This is my system, right? System of linear equations.
Yes.
Suppose A is invertible. A is invertible, which means that A inverse exists, right?
Yes.
Yes.
What can I tell about A inverse of AX? This is going to be A inverse B, right? I'm multiplying
Yes,
by
ma'am.
A inverse on both sides.
3
What is this?
X.
A inverse B. So Do you agree that when the matrix is invertible, this is the only solution to the system of linear equations?
Yes, ma'am.
Yes.
Yeah. So now if B is 0, then X is 0, right?
Yes.
Yes, ma'am.
Because A inverse of the 0 vector will be 0. Now, what I already know is X is 0. I have this. Now
Yes,
can
ma'am.
I pre-multiply by A?
Yes, ma'am.
So B is 0, right? Like, this is the reason. If A is invertible, I have only one solution, and that solution is this.
Ma'am, could you repeat the last one?
Yeah. So now you agree that I have only this as the solution, right?
Yes.
Yes.
And I already know X is equal to 0 is the solution because of the determinant of AXI being 0. Here, we already have this.
Ma'am, it's look like a homogeneous equation. Homogeneous
Yeah.
linear
If B
equation.
is 0, it is a homogeneous equation. Yes. System of homogeneous equations.
And all these AXIs will then be 0.
No, AXIs need not be 0, but their determinants are 0.
Sorry, yeah, the determinants would be 0.
It's given, no? That's what is given. Determinant of AXI is equal to 0 for all I. So from that, I know the solution, right? When determinant is not 0, I know the solution.
Yes, it will be 0. All X's would be 0.
Yeah, and that is the only solution that I have. A inverse B is 0, right?
Right.
So I'm just pre-multiplying by A on both sides. A times 0 is B.
So I mean, we lead to this situation would be only and only if B is 0.
Yeah, that's what we got, right?
Yeah.
That's what we are getting. We are telling that B has to be 0.
And suppose B is
So
not
this is
0.
right. Huh?
Suppose B is not 0.
If B is non-zero, then A inverse B is non-zero, right?
And then in this case, is it a unique solution?
X is the unique solution. Means A inverse B is the unique solution. Do you agree to this? B is non-zero implies A inverse B is non-zero?
Yes.
Yeah. So what is A inverse B? That is the solution to the system, no? X.
Yeah, which we found to be 0.
0. Yeah. So it will be a contradiction. Is it clear?
Ma'am, actually, that one I was not clear. Can you please repeat that one, please?
Which one?
Ma'am, that one we should explaining the options now. Using that just before that. Yes, this
Option
one.
2 and 3 is clear, right?
Yeah, that is clear. But
So option 4, determinant of A is not equal to 0, I can apply Crammers rule, right?
Yes, ma'am.
And if I can apply the Crammers rule, what is my solution?
Ma'am, here actually what you explain, no, I did not, connect you. Just this line is clear. That xi is
So
equal to.
X is equal to 0 is the solution, right? If I can apply the Crammers rule.
Yes.
Okay. So now, if I have AX is equal to B, suppose the matrix A is invertible, I can pre-multiply by A on both sides, A inverse on both sides, right?
Yes, that is it.
So I'll get X is equal to A inverse B. Right?
How it is, man? Like A inverse.
I'm just
Okay,
pre-multiplying by A inverse on both sides.
Yeah,
A inverse of AX is A inverse of B.
Yes, I got it. That AX is equal to B, so A inverse multiplied both sides, that becomes A inverse B. Okay.
Excuse me, ma'am.
Yes.
Here,
Ma'am, from this, how did you
given that
conclude? Ma'am, from this, X is equal to A inverse B, after getting this, how did you conclude the next one?
Yeah, 1 second. There was someone else with a doubt in this step, I guess.
Yes, ma'am. Ma'am, in the question it was given that A determinant of A is not equal to 0. So you are using that you are using the inverse concept because of that, because determinant of A is not 0.
Yeah.
Okay, ma'am. Got it, ma'am. Got it. Clear.
Okay. So now we are at this stage. So you agree that if the matrix is invertible, I have only one solution to AX is equal to B, and that is A inverse B, right?
Yes.
Yes. So there was someone asking a doubt in this step, right? Do you agree that A inverse B is the only solution to AX is equal to B?
Yes.
Who was asking the doubt?
There was someone else also.
Who was asking the doubt?
Ma'am, Ramakant is right.
Okay. So did you understand that A inverse B is the only solution?
Yes, ma'am.
Yeah. Now I know that X is equal to 0 is the solution, right? Because of that determinant of AXI non-zero, this portion, right?
Yes, yes, ma'am.
Okay. So now this is my solution, right?
Mm-hmm.
Now can I pre-multiply by A on both sides?
Yes.
That's how I get A. B is equal to 0.
Okay, okay, okay.
Okay. So any other doubts in 2.2?
Ma'am, hello, ma'am.
Yes.
Ma'am, here we have taken A into A inverse is equal to 1, no? But that case we are
Identity.
not taking. Yeah, here we have taken A into A inverse is equal to identity matrix. But that case we have not taken, madam. Like D is equal to
No.
A
Here
into
we
A
are. A and A inverse are close to each other. That is why we are allowed to do that.
Okay.
There they were not next to each other.
Okay, they are close
Here.
to each other.
Here they are not next to each other. No, there is an A in between. P and P inverse.
Okay.
Yeah. If I had like this, we could have taken. That's what I said. But we don't have that.
Okay.
Yeah. So yes. Any other questions? I guess all the others are simple, right? You can do it on your own. Yes.
I have one question, not from week 2, but from graded 1, wherein we had the first question wherein there was a matrix given of size 2 by 3 by 2, and the resultant matrix C was given. So in that 5 options which were given, there has to be a unique matrix A satisfying the property. But on the other hand, the answer says that there has to be infinitely many matrices. Can you just put some light on that? I didn't get how there could be
Which
many
matrix?
matrices. A graded assignment 1, first question.
No, it will not be the same for everyone. It's randomized.
Okay.
Did you check the solutions? Is the solution uploaded?
Okay. I'll have not gone through that
Yeah,
one.
maybe you'll check because in the solution we give solution for all the questions.
Okay.
So
Okay,
all
I'll check.
questions will be there.
Okay. Thank you.
Okay, so yeah, we know how to find the inverse of a matrix, right?
Yes.
What do we do first?
First, we find the
Determinant of
We find the determinant of the matrix, and then we find the adjoint matrix. How do we get the adjoint matrix?
By minus.
Transpose of the cofactor
Transpose of the
matrix.
cofactor matrix.
Yeah, so we first find the cofactor matrix, take its
cofactor.
transpose and all that.
Take transpose of that.
Yeah. So can we quickly calculate the inverse of this matrix, or at least some entries maybe?
Yes.
Well, okay, what is the determinant first?
Expanding upon the first row, it will be 3,
Minus 3.
0, 1, minus
1 into 1 minus 2 into 1 plus 3 times 1 into 1 minus 2 into 0.
0.
So this is 0, 1, 3 minus 1 plus 2. This is 3. This is 0 minus 1 minus 3. 2, right?
Yeah.
Yes,
3
ma'am.
minus 3, 2. Okay. Okay. Now cofactor matrix.
Minus 1.
Minus 1.
Minus 1.
Plus
minus 1. And then another minus. So plus 1.
1.
1.
1.
Minus
2 minus 1.
2 minus
But
3.
then
Plus 1.
Then again minus, so plus
2 minus 3. Minus 1.
3 minus 6 minus 3, right? Okay. Oh, not this one. This one. 3 minus 4 minus 1, but there's already a minus, so plus 1.
plus 1.
2.
2.
2. Zero.
0.
Minus 2.
Minus 2.
Minus 2.
Okay, so what's the adjoint?
Minus 1, 1, 1. First column. 1 minus 3, 1. 2, 0 minus 2.
And what's the inverse?
2, 0 minus 2
Minus
it
2,
is.
ma'am.
Oh,
So it is 1
1
upon
by
2.
determinant into the adjoint.
Yes, ma'am.
Yeah. So this is the inverse of that matrix. So what properties does the inverse have? What is A inverse?
1. That is identity. Identity
Identity
matrix.
matrix.
Sorry.
The identity matrix. And what is the determinant of A inverse?
1 upon
1
determinant
upon
of A.
1 upon determinant of A.
Yeah. And then there are some properties related to determinant of adjoint and all that, right?
Yeah.
A into adjoint of A is what? Determinant of A into identity. All this stuff is there, right? Some properties related to adjoint. So most of the questions are related to all these properties. This question. How do we do this? A is equal to A inverse. If A is equal to A inverse, what can we tell?
Determinant of
A or A inverse equal.
Determinant of A is equal to 1 by determinant of A, right?
Yeah.
Yes, ma'am.
So determinant of A squared is equal to 1. So determinant of A can be
1.
1.
plus or minus
Plus
1,
minus
right?
one.
Minus 1 is also
Yeah, yeah.
allowed. Yeah.
Yeah.
So this is wrong. If A is equal to A inverse, should A be the identity matrix?
not always.
Not necessarily.
No, ma'am.
Not necessarily, because we know that determinant of A can be minus 1 also.
Yeah.
Yeah. If A is equal to A inverse, should A squared be identity?
Yes, ma'am.
Yes, ma'am.
Yeah. You just multiply. What is A squared? A into A. But A is equal to A inverse. So it has to be identity.
Yeah.
If A inverse is equal to adjoint A, then determinant of A must be 1. What is A
2.
inverse? Yeah, 1 by
1 by
determinant
A
of A into
Adjoint
adjoint of A.
A.
But this is equal to adjoint of A, which means this has to be 1.
Yeah.
Okay. Any questions from the activity?
Ma'am,
Yes.
ma'am, could you please go back to where you were writing just now?
Okay.
Ma'am, I didn't understand the last two steps. the a square equals to a times a equals to a times inverse of a.
That's because it's given A is equal to A inverse.
Oh, okay. Thank you, ma'am.
This is for option 1. This is for option 3. This is for option 4.
Okay, ma'am.
Okay.
Thank you, ma'am.
Here you just calculate the inverse and all that. Here it's a system, inverse, determinant. Yeah, so this is related to that, right? If AX is equal to B, if A inverse exists, then the solution is A inverse B, right? So using that, we can do this problem. What is a homogeneous system of linear equations?
And B is equal
0. Yeah. A system of linear equations is homogeneous if B not equal to 0. That's false. Non-homogeneous if B not equal to 0 is true. Could you do 3 and 4? Maybe you should try. If you haven't done, you should try. And there are sessions in the future to ask doubts.
Yes, ma'am.
Yeah. And then these are all simple. Okay, fine. So shall we stop the session so that you get a break before the next one?
Yes,
You
ma'am.
can ask
I
doubts.
just have
Yeah.
conceptual doubt from week 1 because I hadn't attended week 1 session.
Okay.
Yeah, so I understood how to see that
So those, we are not going to discuss any more concepts. So you can leave. Those who have doubts, you can stay back and ask doubts. The others can leave.
Okay,
If
ma'am.
you don't
Thank you,
have a
ma'am.
doubt. Yeah. Thank you.
Okay, ma'am.
Okay,
Thank
fine.
you.
So
Ma'am,
what was the week 1 doubt?
Yes, ma'am. So I understood that how to see that whether it is linearly dependent or not in a vector form, but I didn't understand that how we will identify that if there is in equation form, if it is written into an equation.
What is linearly independent? Week 3 or week 1?
Week 1.
What was linearly independent there? Week 1, linearly independent. What was that? With respect to what did we discuss
Let me check,
linear
ma'am.
independence?
Then after I'll ask. 1 minute.
Okay.
Ma'am, I have a question, ma'am.
Yes.
So with respect to that activity question about did D equals PAP inverse, that which we were discussing.
Okay.
I wanted
Okay.
to say, but like we kept getting interrupted, so I'm waiting. I was thinking like we cannot change the order of multiplication of matrices. That is correct, right, ma'am? But the determinant we can break up, right? Like determinant of
Yeah,
D.
like this.
So yes. So from that only we can prove, right? Like
We can
determinant
prove
of
that
A.
determinant of D is determinant of A, but we cannot tell A is equal to D.
Determinant of okay, yes. Determinant of D is equal to A, that we can say, but whether the original matrices are same, that we don't know.
Yeah.
Okay, now I understand. And ma'am, pivot variable and leading term is same thing.
No, the column where the leading non-zero term occurs, that variable is called the pivot. No, in the sense wherever you have a pivot corresponding to that. What was your question? Pivot variable.
Yes,
No.
in tutorial sir says pivot, but in lectures we have a leading term.
Yeah. Pivot and leading term. Yes, leading non-zero term is pivot.
Same thing.
Yeah.
Okay. And one more thing, I mean, you said you will discuss it next class, but still, just because I've watched about echelon and row echelon, can I ask?
Yeah.
For like echelon and row echelon, what I understood is that both are similar almost. The difference is in the reduced one, wherever we have leading one, that entire column will have 1 or 0 only. Correct?
Yeah.
And if any other term, it is not leading term, then there it can have any other term. That is
Yeah.
correct.
So the column will anyway have. Oh, okay. Yeah.
Like if it is
So
a
this
square
is
matrix, then it mostly becomes identity. But if it is a rectangular matrix,
not
then the fourth
necessarily identity. This can also happen.
yeah, if the
This
third
is
row is all zeros.
this is row echelon form.
This is row echelon.
Yeah, this
And
is
if we make
reduced because this is a pivot, right?
Pivot, right? And above that it should be all 0. And the
Yeah.
second one is not the leading one, so it can be one above that.
Yeah, this can be anything.
Okay.
These are my pivots.
1 and 1. And so the variable corresponding to these two will be independent.
Will be dependent. Corresponding to pivots, they'll be dependent.
I always
when you don't have a pivot, that will be independent.
The one without pivot will be independent, and so we can assign it any random value.
Yeah, independent ones you can assign random values.
While solving questions. Okay, okay. Well, like, is there? Can you show any way to just correlate with pivot dependent? I always mix up these two.
No, it's obvious, no? So you have the system being reduced to this system now. Some B1, B2, B3, whatever.
Right.
Some values. So now the system becomes x1 plus x2 plus x3 is equal to B1. x2 plus x3 is equal to B2. 0 is equal to, okay, this has to be 0. 0 is equal to 0. Yeah. So x2 becomes B2 minus x3. Right? There's no pivot here. So x3 is independent. You choose any value for x3. Once you choose a value, x2 is fixed, right?
Okay, so x2 depends on the value to x3.
Yeah. Because there is a pivot here, it is dependent on the other variable. Similarly,
by
x1.
X1.
Yeah.
Okay. And ma'am, that
so x1 is dependent on these values.
X1, right. So we start from the last column, last variable, and that will show us that the first two were dependent on that last one.
Yeah, that's why we are doing this, no? So that we can do this backward substitution.
Yes.
Yeah. If this last entry was 1, then I would have got the value of x3.
Yes, ma'am.
Yeah. So in that case, it would have also been dependent. It's not independent because there is a pivot there.
Ma'am, I remember just because you wrote it, it flashed suddenly. In the lecture, sir was saying something. He did not write it. That if this is 0 and here some other value is given, like, can you scroll up a little? B3. If B3 was there, but on the coefficient matrix we have 0, then what does it mean for the system of equation? No solution.
0 into x1 plus 0 into x2 plus 0 into x3 is B3. I know the left hand side is 0, right?
The last one,
yeah.
A33.
So this is non-zero. This is 0, but this side it's non-zero, right?
B3 is there, non-zero.
0x1 plus 0x2 plus 0x3 is equal to B3.
Yes.
I know this is 0, right?
Right, ma'am.
So these two cannot be equal if this is not 0.
So the whole system
in that case, there'll be a no solution case.
No solution. Okay. Thank you, ma'am.
Yeah.
Ma'am, can I ask out?
Yeah, sure.
Ma'am, one thing I'm confused when we multiply scalar from matrix, so we multiply whole the matrix with the scalar.
Yeah.
When we eliminate the scalars from the matrix, we means we eliminate
Why
all
are we
the
doing it row wise, is it?
Pardon me?
Why are we eliminating it row wise? Is that your question?
Means we solving the matrix or finding the determinants or something. So when we eliminate the some scalars, some common from all the rows, then we each rows we multiply.
Yeah. So your question is this, right? A, B, C, D. Alpha times A, B, C, D is alpha A, alpha B, alpha C, alpha D. Then why not determinant of alpha A, alpha B, alpha C, alpha D equal to alpha times determinant of A? This is the question, right?
Yes, ma'am. When we eliminate the alpha, if we determinant is alpha A, alpha B, alpha C, alpha D, if we eliminate the alpha, so it is alpha square.
Yeah.
Outside the.
You're asking why, right? Because when you replace one row with alpha times the row, what is the effect on the determinant?
No change.
No. Alpha times means it gets multiplied by alpha, no?
Yeah.
Yes.
But what have you done to the matrix? You have multiplied both R1 and R2 with alpha, right? So here it's one alpha determinant of A, and then here it will become alpha times alpha determinant of A, right?
Okay.
Yeah.
Ma'am, there is a difficult to me because it's a long gap from my studies, about 26 years.
Okay.
So I would find difficulty in finding the determinant if the matrix is having the very long means how to find it. There's a activity question 1.4, 10 and 8.
1.4. Yeah, so here you shouldn't be actually calculating. You use the properties of determinant, reduce it to use certain row operations such that the determinant does not change and find the value of the ultimate matrix.
So once we find the zero, how to solve this?
A, B, C, B, C, A, C, A, B. So now if I want to make this entry 0,
yes,
I can do R2 is R2 minus R1, right?
R2 minus R1, okay.
I'll replace R2 with R2 minus R1.
Okay.
When I do this, is the determinant going to change?
Yes.
No, right? This row operation does not change the determinant, no?
Yes, ma'am.
Similarly, R3 is R3 minus R1. This is also not going to affect the determinant.
Okay.
Now my matrix becomes 1, 0, 0, A, B, C, B minus A, AC minus BC, C minus A, AB minus BC. Finding the determinant of this matrix is simpler, right?
Yes, clear, ma'am.
Expand along the first column. This is that, and then 10. What is 10?
Similar, we do that one.
Here you have this format A, B, C, C, B, B, C, A. So you do something and make it simpler.
Is it we going to 11, 12th NCRT? Yeah, is it
There are a
okay?
lot of problems like this there, right? You can try out all that.
Okay.
Yeah.
Actually, it's a long gap for me now.
Yeah, it's completely understandable.
Ma'am, why we always use just row operation? Can't we use column operation instead of that?
Yeah, to calculate determinants, you can use column operations to make it simpler. But why we use row operations always is when we get into this echelon form thing,
Yeah.
we are actually trying to solve a system of equations. So,
So
say
we
I have
can't use
expressed.
it. Otherwise, the system will change, right?
Yeah, it'll get disturbed, no? The system is getting disturbed when you use
But
column operations.
in the form of determinant, we can use column operation.
Yeah, you can do any operations, row or
Similar
column.
as row operation, right?
Yeah. Suppose you had 1, 1, 1,
Yeah.
A, B, C. You could have done column operations and made these 0.
Yeah. Right.
Yeah.
Ma'am, I has one doubt about invertible. I didn't understand that what is invertible.
Invertible means inverse exists. That's
Inverse
it.
exists, yeah. That's all.
Yeah.
That is
So
called
for the
invertible.
inverse to exist, determinant has to be non-zero.
Yeah. Then inverse will exist and then it will call as invertible, right?
Yeah. Invertible or non-singular.
Okay, ma'am. It means singular means determinant will be equals to 0.
0, yeah.
Ma'am, there was this question you had done with C1 plus C2, the determinant, and then you expanded. I was not able to keep pace with the solution.
This one, is it?
No.
Or yeah, I had done some C1, C2, C3, C4. C1 plus C2, C2 plus C3, that one, right?
Yeah. I just wasn't able to understand the solution and the expansion.
So did
Yeah,
you
this one.
understand the first thing that I said? This one, did you understand?
Yes,
Determinant.
the basic
You
one.
just
Yeah,
split.
I did.
You
Yeah,
keep
I
the two
understood
first
that.
columns as it is. Yeah. So that's what we are doing here.
But I couldn't understand the splitting part of it.
So what I did was I kept the second and third column as it is, split the first column. So the determinant is going to, so I can split it like this, right? Determinant of C1 plus second and third column as it is,
Yes.
plus determinant of C2 plus second and third column as it is.
That I understood. That's the third line I could not understand.
You do the same thing, keep the last column as it is. You'll get a split and you'll get, this will become two matrices, right?
Yeah.
And then after that, I can split this and that's going to become two more, right?
Okay.
So ultimately, I'll have 4 matrices out of this. That's what I wrote here. I skipped a step in between.
There'll be 4 matrices.
Yeah. 4 from the first matrix alone, 4 from the second matrix.
Oh, that means, these are so many. Okay.
Yeah, I'm getting 8 matrices, of which 6 matrices have 0 determinant because they either have, they will have same columns. 2 columns will be same.
Okay, 8 matrices. Okay, yeah, because of the combination. That's why I did not understand. And then there would be one. There would be one which would be the repetition. Just the rows would be interchanged.
Yeah, columns.
Sorry, the columns would be interchanged. When we interchange columns, then the sign changes, right?
Yeah, but then there are 2 interchanges here, so it's the same.
Okay, so 2 columns interchange with each other. Okay, so twice it happens.
C1 is interchanging with C2, and then again C1 is getting interchanged with C3. So there are 2 interchanges that have happened. So the sign,
So that is something also we have to take into account, that the sign changes twice.
Yeah, exactly.
So effectively, then the determinant of C1, C2, C3 becomes equal to determinant of C2, C3, C1.
Yeah.
Okay. Thank you, ma'am. I understand it better now.
Okay. So shall we close?
Ma'am, one sentence. No?
Yes.
I mean, the sir said something like a single equation can have only one independent variable if at all. meaning like only one.
Independent variable. Okay. Can
Yes,
you
ma'am.
speak a little louder?
Yes. It said in the
Huh.
lecture said that a single equation can have only one dependent variable if at all.
Yes. Yeah.
Can you explain
So
this?
you have only one equation, right?
One dependent. Oh, because the leading
One
term is only
equation.
one in
Yeah.
each column.
That's it.
Okay.
No,
Yeah,
no.
because this.
In each column, in the sense, yeah, you have only one equation, right?
Yes.
A3x3 is equal to some b1 or b. Okay, something equal to b. So
Right.
I can write one variable in terms of the other two variables, right?
X1 equals right. We're moving to other side.
Yeah. If a1 is non-zero, I can write x1 in terms of x2 and x3.
X3. Yes.
Yeah. I cannot write two variables. Means, yeah, in the sense that your matrix is going to be this a1, a2, a3. This is your matrix, right?
Yes.
Because you have
This is
only
the
one equation and three
coefficient
variables.
matrix. Right.
Yeah. Equal to, this is a number. B is a number, 1 cross 1 matrix, right?
Yes, ma'am.
Yeah. So when you do, there's only one leading term, no, as you said.
Yes, one A1 single one variable.
Yeah.
If at all. Like if we have like three sets of equation, then it is not valid there. Or there also.
No,
Should be
in
there
three
also
sets of
valid.
equations, it's different, no? You can have multiple leading terms, no? Like we saw an example, no? Where is that?
The previous one.
That row reduced or reduced thing. Where
Like why did he say if at all? That's what stumped me.
if all the three coefficients are 0, then there's no leading term at all, no?
Okay. Well, then there's no equation only.
Yeah.
A0
This is the equation then.
Okay.
Yeah.
So if there is dependent, it will be only one in each equation. Got it.
Okay.
Thank you, ma'am.
So shall we close?
Yes, ma'am.
Okay, then good night. See you all.
Ma'am, can I ask one question?
Yeah, sure.
I understand dependent variable that you just explained a bit earlier, that in matrix form or determinant form, how we understand that whether it is dependent variable or not.
Okay.
But I don't understand how will we understand if it is written in an equation form like ax1 ax2 type, that whether it is independent.
So did you watch the lecture on row echelon form?
Yes, ma'am.
So you put it in the row echelon form whenever you have a leading non-zero entry. That is, wherever you have a pivot,
Yeah.
the variables corresponding to that are going to be dependent, right?
Yeah. So, ma'am, that is the only way we can understand.
Yeah. That is why we do the row echelon form, to identify which are the dependent variables and independent variables.
Okay, ma'am. Ma'am, let's say C is an independent variable, so we can take any value for C.
Yeah, any real number.
Any real number we can take.
Yeah.
And
so whenever you have independent variable, you're going to have infinitely many solutions, right?
Yes, ma'am. Yes, ma'am. Correct.
Yeah.
Yeah. And other variable will be dependent on that.
Yeah. It depends if that is the only.
Yeah. Okay, ma'am. Thank you so much. It was a beautiful session. Thank you so much.
Ma'am, free variable is also independent variable, right?
Yes. It's just another term for independent variable.
Synonym for that.
Independent. Okay. Thank you, ma'am. Good night,
ma'am. Thank you. Good night.
Yeah. Good night.
Thank you, ma'am.
Good night.
Good night.